Dear students of BSc Part First Year, Government Dungar College Bikaner, I am teaching you the second paper of physics according to the syllabus prescribed by Maharaja Ganga Singh University Bikaner. In the last lecture, I introduced you about the mutual induction and coefficient of mutual induction. I defined mutual induction M is equal to mod E2 upon di1 upon dt, dear students, and I mentioned that if the rate of change of current in the primary circuit is 1 ampere per second, then magnitude wise M is equal to the induced EMF in the secondary circuit. M is equal to E2. Dear student, using this criteria or concept, we can determine the coefficient of mutual induction for different circuits. I will give you very interesting examples to you today. The first one is that in examination it is asked that find the coefficient of mutual induction of two concentric coils let me specify that there is one coil of radius R2 and number of turns in it is N2. There is another coil of radius R1 having number of turns N1. They are concentric at O and coplanar as well. So according to the geometry, if a current I1 is passed through the coil of radius R1, then magnetic field associated with it is mu0 N1 times I1 upon R1. Dear students, due to this magnetic field, the magnetic flux associated to each turn of the other coil is equal to B1 multiplied by area of cross section. Since there are N2 turns, so I can say total flux associated is N2 multiplied by B1 into pi R2 square. I will put the value of B1, so I shall get mu naught N1 N2 pi R2 square upon 2 R1 into I1. And as I told in my earlier lecture that comparing this with phi 2 equals to mi1, I'll get the coefficient of mutual induction M to be nu naught N1 N2 to R1. This is how one can calculate the coefficient of mutual induction for the two concentric planar coils. Now I give you a very interesting example, or you can say numerical, which oftenly in your earlier classes you were afraid of such numericals. Here it is. Suppose there is a current carrying conductor carrying current I. I will write down the question later on. And there we have placed a rectangular closed loop of width A, length A, width B at a distance D from it. One arm of the loop is at a distance D. So I can frame the question like this, that as shown, a rectangular loop is placed at a distance D from a current carrying conductor. Find the coefficient of mutual induction. Now, dear students, you can frame a concept that this infinite long current carrying conductor carrying current I is located at a separation D from the conductor. So how shall I do? This question is, I will consider a small element of width dx at a distance x from the conductor. This is the way to do it. So magnetic field, it is the solution I am speaking. Field at distance x from the conductor is B equals to mu naught I upon 2x. Now the area of this element is B dx, small b into dx, width into length. So flux, hence flux through the element, d phi will be nothing but b into b dx. So total flux associated I will calculate. Total flux, dear students, you can calculate integrating d phi. The distance will of course change from d to d plus a. I am writing the value of b, so it will be mu naught I b upon 2x dx. Now almost all of you easily can pick that 1 upon x integration has a value log x, so it will be mu naught I b and log x. This will be divided by 2, of course. The limits will be from d to d plus a, and I will get mu naught b log x upon 2 d plus a upon d.